This video is going to set up how to predict the products of a single replacement reaction. So where we left off, we were able to look at the beginning or reactants with the products of a reaction to determine if it's a synthesis, decomposition, single or double replacement, and finally combustion reaction. So in this class and at this level, what we expect you guys to be able to do, and this is going to start with just single replacement, is that you are able to look at a reaction and predict the outcome of the said reaction. And so if you take a look at this little review slide, a single replacement reaction, you can see that one component of it, the single part of it, is that you have an element on its own. So carbon starts out, or excuse me, not really carbon, but letter C, that green atom on the reactant side is on its own. As it goes through the reaction, A is now on its own, and element B and C are combined together. And so the single part of it is that you again have one reactant that's an element ending with a product that's an element and a new compound from the reactant side. So what we're going to use today is a handout called an activity series, and what this does is lists out the reactivity of both metals and nonmetals, and it's ranked in order of increasing to decreasing reactivity. And so again, that handout is much like a periodic table that we expect you to be able to use that list to then work out if a reaction will move forward or not. So we can look at the reactivity series or activity series, whichever way is kind of potato on this, that there's two ways of looking at it. So the first thing is the activity series lists out metals. And again, if you remember, metals like to give away electrons, so they like to make cations. And so what we have is a listing of, again, the metals that make them up. And so here is that activity series. So when we take a look at that handout, you can see the left-hand side is the breakdown of our metals, starting with lithium at the top as being the most reactive metal, and you look all the way at the bottom, gold is the least reactive. And so while I'm on this screen, you can see the right-hand side is a listing of the non-metals. Same idea, fluorine is at the top of the list, so it's most reactive, followed by iodine being the least reactive. So like I said, halogens, those are those nonmetals that we have on the right-hand side of that activity series. And again, it's listed from increasing to decreasing reactivity. So the first thing is not all reactions take place, especially with single replacement reactions. So you can't combine just any metal or halogen with a compound and something is going to happen. So the first thing is we have to use that activity series to decide if a reaction can even take place at all or not. So in a single replacement reaction, you have to look at the single element and compare it to the reactivity of the element that it's trying to replace in the compound. So if you have a metal reacting with a compound, you have to see if that metal is more or less reactive than the metal in the compound. And so as we look at the examples, this will begin to make a little bit more sense that what I'm talking about. For a reaction to happen, that single element has to be more reactive or higher up on the activity series list than the one that's already in the compound. If it's less reactive, no reaction can occur. And like I said, you'll see examples of this as we take a look at the practice problems. All right, so what I do to break these apart is the first thing is I have magnesium. So if you want to take a minute and pause this video, you definitely are going to need your periodic table with your charges and then your blue or your polyatomic list, but the original one that I gave you is on blue paper. So the first thing when you look at this is right here I have the states of matter. This part doesn't impact how we solve it. All it's doing is telling me that my magnesium is in the solid state and that my zinc 2 nitrate is aqueous, meaning we dissolved it into a solution. And so we're going to see that with our lab. So what I have to decide first is if what magnesium is going to try to replace. So if you take a look at your periodic table, you need to figure out what charge magnesium makes. And if you look at your table, it makes a +2 charge. So that means magnesium, because it's a cation, is going to try to replace the cation in the compound. If you remember back to our chemical naming, the cation, the positive charge is always found first. So what we're looking for is, can magnesium replace zinc? I'm going to change the screen back to the activity series, and then I'll change it back to this. So as I take a look at this, let's see here. This isn't showing up for you guys. All right, so I got the screen fixed. So if you take a look, we're looking to see if magnesium is more or less reactive than the zinc. So magnesium is here, zinc is down here. Whichever element is further up the list is more reactive. Magnesium is above zinc, therefore magnesium is more reactive than the zinc. That's really important because that tells me the reaction can take place. So I'm going to jump back into my PowerPoint to that example we were working on. And I'm going to swap my screen over. There we go. So what I had established before I had to change my screen over is that magnesium is a +2. And that was going to try to replace the zinc because that was a cation. We discovered that magnesium is more reactive than zinc, so that means my reaction is going to take place. So what we expect you to do is to be able to predict the outcome or products that are formed from this reaction. So the element, I like to write the one that's now on its own, the single part of it first. So zinc got replaced, so zinc is now on its own. I now need to predict the outcome of my compound. You need to start over with charges like we did back in January with our chemical naming. So I know that magnesium is going to combine with NO3. So again, if you haven't found your polyatomic list, get that out. So magnesium we established is a +2 charge. It's combining with NO3. When you look at the polyatomic list, you discover it's a -1 charge. So this is a little bit of a blast from the past. So again, if you recall, we cross charges. I bring down a 1 to my magnesium. I'm bringing down a 2 to the nitrate. Recall, because it's a polyatomic, it's going to go in parentheses, and that subscript is going to go outside. Again, the reason why that 2 is there is because of the charge of the magnesium. The last step is to balance it. Because magnesium and zinc have the same charge, that nitrate gets a 2 on both sides, so the equation is balanced. Moving on to the next example, magnesium is in the same boat. It's still a +2 charge. So what we have to look at and establish is what is magnesium going to try to replace? It's the cation. The cation in my next reaction is silver. You're going to go to your activity series. When you take a look at your activity series, you have to establish which one is more reactive. So let's see if this will work. This is not going to work for me. So I'm not able to pull both screens up and not lose my writing. So what I need you guys to do is look at that activity series. Magnesium and find silver. Which one is further up the list? That one is going to be the magnesium. Therefore, magnesium is more reactive than the silver. That means the reaction is going to take place. That means that silver will now be on its own. The last step is figuring out your new compound. So again, NO3, like before, was a -1 charge. So the formula for our compound is basically the same thing as above because we have the same elements with the same charges. I'm going to go ahead and get rid of some of this writing on this equation so I have some room. The difference is this one is not balanced. I need to go ahead and add some coefficients to it. My magnesiums are equal, my silvers are equal. Nitrates are not. I'm going to add a coefficient 2 on this side to balance it out. By changing that, that gives me 2 nitrates, but it also gives me 2 silver. I need to place a coefficient of 2 in front of the silver. I now have a balanced equation. Taking a look at the last example working with magnesium, if you take a look, we have magnesium, still a +2 charge. So what's it going to try to replace? That's going to be the lithium. Again, metals replace metals. Like charges replace like charges. So now we have to figure out if this reaction is going to take place or not. If you take a look, if you find those two elements, you'll discover in this example magnesium is below lithium. Therefore, magnesium is less reactive than lithium. Therefore, this reaction cannot take place. So this one is a really easy one to work out. And we're just going to say that it's no reaction because, again, magnesium is less reactive than our lithium. All right, so moving on to the last set of problems. This side, we kind of changed things up a little bit. So to start out, I'm going to mention this acronym, and the acronym is called Hoefnkleiber. This represents the 7 elements that are diatomics. These 7 elements are never found alone in nature, and so by saying Hoefnkleiber, that helps you keep track of the 7 elements that we're talking about. So for example, here when we take a look at chlorine, we don't see it as just Cl, but we see it as Cl2. Same thing down here with bromine, it's one of the 7, so when it's on its own, we write it as Br2, not just Br. So like we started with the left-hand side, the first thing you need to do is figure out if the reaction is going to take place. So if you take a look at chlorine in the periodic table, you discover chlorine is a -1 charge. So again, this is going to be a little bit different than the right-hand side, or excuse me, the left-hand side, in that chlorine is going to replace the like charge. So we have to compare now chlorine to bromine, because bromine is the anion in the compound. You're going to go to your activity series, and we're going to be using the right-hand side. You're going to find chlorine and bromine, and you have to discover which one is more reactive. If you take a look, chlorine is further up the list than bromine, so that means chlorine is more reactive than bromine. That means the reaction is going to take place. So now we can go ahead and predict the products of the reaction. So bromine will now be on its own. Bromine is Hoefnkleiber, so the formula for it will be Br2. My other product then is going to be my compound. Again, think of the things we use with chemical naming. Your positive goes first. Our positive or our metal is sodium, so it's Na+1. Chlorine we established is Cl-1. Our charges cross out and cancel, so we get NaCl. The last step is just a balance. If you follow the pattern, it's a 2-1-2, and that's a balanced reaction. For example, number 5, notice here the Fe, I gave you the charge because it's a transition metal. Iron is a cation, so it's going to try to replace the copper. Iron is more reactive than the copper, so that means the reaction will take place. So what I'm left with is I like to write the element that's on its own first, which is copper. Copper is not Hoefnkleiber, so I just write out Cu. Iron is my cation. Sulfate is what it's combining with. They have like charges, so it cancels, so it becomes FeSO4, and I now have a balanced equation. The very last example, I have bromine. Again, if you take a look, bromine is an anion, it's a halogen. It's going to try to replace the halogen or the nonmetal in the compound, that being the chlorine. You're going to take a look at your activity series and determine which is more reactive. Bromine is lower on the list than chlorine. That means bromine is less reactive than chlorine. That means the reaction cannot take place. So all you need to do is put no reaction and you are done. So this was a quick run through on how to predict the products and balance the products of a single replacement reaction.